What I wanted to do here before we got into anything new today is I wanted to give you a problem to try out to see how you're doing with that order of operations stuff. I want you to try that problem in your notes quick. See what you come up with, and we'll go over it here in just a second. We had to rush a little bit at the end of class yesterday. That's why I wanted to circle back to this one. This line across here, most people recognize it as meaning divide, but it's what's called a fraction bar. And it does mean to divide, but it's also a form of enclosing symbol. It is telling us we have to do everything that's on top first, then we have to do everything that's on bottom, and then we can divide. So an enclosing symbol is any symbol that separates one part of the problem from another. So let's do the top first. So in that portion of the problem, what needs to be done first?
4 squared.
The exponent, 4 squared, which is 16. Now there's no more exponents. What would be next? Multiply and divide left to right. So we've got 8 times 12 is 96. What would be next?
3 times 16.
3 times 16 is 48. And then subtract. Yeah, 96 minus 48 is 48. So the top of this becomes 48. Now we have to do everything on bottom. Do we have any enclosing symbols down there? No. Any exponents? No. So then we need to multiply and divide. Left to right, we've got the 5 times 7 first, which is 35. Now we also have a division here. 55 divided by 5 is 11. So now we're down to 35 minus 11, 24. So the bottom is 24. Now we can divide. 48 divided by 24 is 2. Now I'm going to let you in on a little secret. Your calculator does do order of operations. It, however, does not do, in most cases, the fraction bar. There is one version, it's the math type version of the TI-30 that will do a fraction bar. For the most part, they won't. So if you're going to try to do a problem like this in your calculator, do it exactly the way I just did it. Do the top first. 8 times 12 minus 3 times 4 to the 4 squared. 8 times 12 minus 3 times 4 squared. Get the 48 and write that down. Then do the bottom. 5 times 7 minus 55 divided by 5. 5 times 7 minus 55 divided by 5. Gives you the 24. Write that down. Then we can divide them out. So even though the calculator knows the order of operations, sometimes it's just not possible to enter it in the calculator the way it looks. Now, if you're really creative or critical on how you put in parentheses and stuff, you can put that into the calculator all in one long piece, and it will do it. But you have to get those parentheses in exactly the right spot. Like I said, there's one version of the TI-30 that's a math type version that actually has that fraction bar in it. You can enter the fraction and put all that stuff on top and on bottom, and it'll do it all at once. Now, one like this example here from the homework that we did, this one I can actually put in the calculator all at once. I've got 17 times 7 minus 4 times parentheses 3 to the power of 3. By the way, for those of you that haven't figured out how to enter a power in your calculator, that caret key that's in red there, that's the one that's the most common one. But some of your calculators have a y to the x or x to the y key. So the third power, arrow out, minus 3 times 2 to the third power. Close my parentheses, plus 7, and it will give me the 114 that we had. So yes, the calculator does know the order of operations, and it does follow them, as long as you can get it entered into the calculator correctly. There are other enclosing symbols that we are going to encounter as we go through the semester. Some of them more or less important than others, but they will be there. Okay, well, today I wanted to start off with a little bit of a discussion on division. A problem that came up in the homework looked like that. 0 divided by 8. What does that equal? 0. To verify, I can do it in the calculator. 0 divided by 8 tells me 0. Remember, 8, when you divide, we're talking about repeated subtraction. How many times can I subtract 8 from 0? I can't. 8's bigger than 0. So that makes sense. What if it were the other way around, however? 8 divided by 0. Well, how many times can I subtract 0 from 8? Well, I can subtract it once. Can I subtract it again? Sure. Can I subtract it again? Sure. I can keep subtracting. Am I ever going to get down to a point where I can't subtract it again? No, I can't. I can subtract it over and over and over forever, infinitely many times. If I tried to do that on the calculator, 8 divided by 0, the calculator is going to give me a nasty message. Your error message may look different than that, but it's still going to say error. Usually division by 0 error or input error or something like that. Calculator doesn't like dividing by 0. That's because we cannot divide by 0. The definition of division, which we hinted at a little bit when we talked about integers yesterday. Division is not its own operation. Division is defined as part of or the reverse of multiplication. So if I give you 24 divided by 8 equals blank. What that's really asking us to do is to fill in the blank in a multiplication problem. That's asking blank times 8 equals 24. Well, what number can I fill in here? Yeah, 3. 3 times 8 is 24. Therefore, 24 divided by 8 is 3. If I ask 12 divided by 0 equals blank, what that is asking me is what number times 0 equals 12. Well, if I multiply anything times 0, what do I get? 0. That is something called the zero product rule. That's just one piece of the zero product rule, by the way. Is that anything, I'm just going to use the letter A, times 0 equals 0. If we're multiplying by 0, that's the only answer we can get. So there's absolutely nothing that we can put in here to multiply by 0 to get 12. It just doesn't work. You know, some people look at this and say, well, shouldn't that be infinity? Because you can subtract it infinitely many times. Which it kind of makes sense when we look at it as division. But if we remember that division is not its own operation, if we look at it in terms of this over here, infinity times 0, well, how do we know if that's 12 or 8 or 13? Is there a different infinity that when you multiply by 0 gives you 12, so that another one? No, there's only one infinity. So it cannot be done because there's no way you can distinguish if you put something in here to make it 12. Now that idea, that sounds like a very simple concept, but I always like to share a little story. In the late 80s, early 90s, the U.S. Navy first started to experiment with satellite navigation on their ships. And they had actually been using it for several years. What they did is they just put in the coordinates of where they wanted to go, and the system would access the satellites, find the coordinates they were at, and it would calculate from there then the most efficient path, the shortest path to get from where they were to where they wanted to go. They said they'd been using it for years without a hitch. For some reason, well, by some coincidence, on this day, the coordinate that they were at and the coordinate to where they wanted to go lined up just perfectly, so when they did some subtraction and stuff, it gave them a 0. So the system tried to divide by 0. It locked up their computer system. We had a Navy battleship, we're talking a multi-billion-dollar battleship, sitting dead in the water for over 6 hours while they had to reboot the computer system.
Oh, I remember that. Yeah.
It could not move. No, because they tried to divide by 0. There was nobody put a safety into the program so that if that number came out to be 0, that it stopped it. It let it try to calculate it, and it locked it up. It was very humbling to see that. Okay, well, new stuff for today. We're going to touch a little bit on algebra, and we're going to talk about algebraic numbers. First thing we need to talk about is that thing right there. What is a variable? A variable actually has several different roles. Really, all a variable is a letter or some other symbol that's put in there in place of a number. It really doesn't have to be a letter. It's just anything that's put in there to take the place of a number until we replace it with that number. So we could have 5x, or we could have x plus 7. We could have n instead of x. We could have a triangle for a variable. Whatever symbol we want to use to replace that missing number. Now, we're going to stick to letters in here. We're not going to use triangles and squares and whatever, just because it's confusing. But that's all a variable is some sort of symbol that's replacing a number. The role it plays, there are various roles it plays. It can be a formula. Now, in a formula, what that variable is doing is it is sitting there waiting for a value to be assigned to it. So you might have, the area of a rectangle is length times width. A, L, and W are variables. They represent numbers. We just have not given them a value yet. So here they're waiting for a value. So once we find the rectangle or have the rectangle we're going to be using, we can get the length and the width from that rectangle and use them to calculate the area. We could also have it just an algebraic number. And an algebraic number, it kind of takes the place of a place value. It might look like that, 3x plus 2. Here it is just the variable, the x in this case, is just taking the place of like our powers of tens and our place values that we use for standard numbers. And it's there so that we can manipulate the symbols. It can still get a value, a number assigned to it at some point, but it's not a specific application. The last thing that the last one that we're going to discuss at least, role of a variable, is in an equation. In this case, it has a value. It's just the value is not yet known. Very different from up here where we don't know what value it's going to have, and we haven't given it a value yet. We're waiting for a situation to tell us what value to give it. down here in the equation, it already has a value. We just don't know what that value is yet. Here, 2y minus 5 equals 11. Our variable is y, and it has a value. There's only one value it can have. We just haven't figured out what that value is yet. And we can find it. We can calculate it and find it. So we're going to be talking about mostly right now is this situation here, where we're using that variable just to replace an unknown number, a generic formula, generic number. And the skill that we're going to look at here next, I think, is one of the most difficult skills in math. And that is translating words into mathematical formulas. Now, as we move on, this is going to transition. Today we're going to look mostly at taking word sentences and translating them into formulas. But as we move through the summer, we're going to look more and more at taking a story problem and turning it into an equation or a formula that we can work with. But for today, we're just going to look at things like the phrase 7 more than a number. And how would we express that or write that with symbols rather than words? Well, 7 more than. First of all, we know that we're dealing with a 7. And we know that we're dealing with a number. Now that number, that unknown number, can be represented by a variable. Most of the time people use X or N or something like that, but it can be any letter. I could use P if I wanted to. Whatever variable or symbol. I could use a triangle or a bullseye or whatever I wanted to as a variable to represent that unknown number. We're going to choose the variable, the letter P for that variable. So I have 7 and I have P, and now I need to figure out how they're linked together, what the relationship is. Well, more than implies addition. If I said Tim had 8 apples and Pete had 3 more apples than Tim, that implies you're taking 3 and adding it to what Tim had. So we've got the P and we are adding 7 to it. So 7 more than a number implies P plus 7. Would it be wrong if you wrote 7 plus P? Do they mean the same thing? It's still adding. Yeah. If I put any number in for P, let's say I put in the number 9. Well, 9 plus 7 is 16. 7 plus 9 is 16. That works. So these two are equivalent. And the reason for that is addition is something we call commutative. We can change the order of the two numbers being added and it doesn't affect it. Well, what are some other phrases that might be represented with P plus 7? Well, a number plus 7, that would be a variable plus 7, right? A number increased by 7, that would be a variable plus 7, or P plus 7, if we're going to stick with P. Any others you can think of? Well, you'd have to be very careful there. You could do the sum of 7 and a number, or of a number and 7 might be. What that's saying, the sum is saying that you are adding them. Because if you just say 7 and a number, it doesn't necessarily say what you're doing to connect them or to put them together. That's actually a big one. The sum is the word for the result of an addition problem. Again, if you said a number and 7 or 7 and a number, it means the same thing. But technically, if you see a number and 7, it means you put the variable first, usually. Now, a slight difference. You know, I said 7 more than a number. If I say 7 is more than a number, I just changed it slightly. The only difference is the word is. How does that change the way I put that into symbols?
You're making a statement that 7 is larger than the other.
Yeah. 7 is greater than P. I have to use those symbols. Most of the time, we're going to be looking for something like this, not the greater than or less than symbols. If I look at a number decreased by 4, let's say I'm going to use M for the number. How would I write that? M minus 4. By the way, my math lab will tell you what letter to use for your unknown number. Make sure you use it or it'll mark it wrong. It's just saying use P or whatever. It's just part of its programming is it can't just recognize a general letter. So M minus 4. Would it be the same if I said 4 minus M? No. Subtraction is not commutative. The reason being is, like we said yesterday, subtraction is not its own operation. Subtraction is part of addition. If we were to change this, technically M minus 4 would be the same as M plus a negative 4. Remember, subtraction means add the opposite. Now that it's in this form, now it would be commutative because it's in addition form. What are some other phrases that would mean M minus 4? A number minus 4 would do it. Anything else? Four less than a number. The difference of a number and 4, yep. Remember that word difference, that's the result of a subtraction problem. And there are a lot of other phrases that might mean M minus 4, or would give us M minus 4. Let's say I have a number repeated 5 times. There are actually several ways of writing this. Let's say I want you to use D for my number, for my variable. I could just do 5 D's added together, couldn't I? There's a simpler way of writing that. What would it be? 5 times D or D times 5. Now when we deal with algebraic numbers, we a lot of times don't put in the multiplication. We just do 5D and that implies it's 5 times D. Just like if we have 5 inches, that implies that we have that regular inch times 5. There's 5 of them. Could we have done D times 5?
Yeah.
Yes. Multiplication is commutative. So other phrases that might mean 5 times D or D times 5. What would you have? A number multiplied by 5? Five times a number? Does anybody know the word for multiplication, like sum or difference? the product of a number and 5 or 5 and the number. And again, there's several others that would mean 5 times a number. We might have a number split 3 ways. How do we write that? For the number, I'm going to use the letter C. C divided by 3 is one way to do it. Now in algebra, a lot of times we use fraction notation. We just saw that fraction bar in our order of operations as meaning division. So instead of writing out C divided by 3, we might just put C over 3. That is division. Would it be the same if I did 3 divided by C?
No.
No. Division is not commutative. Again, division and subtraction are not their own operations. The division is part of multiplication and subtraction is part of addition. That's why they don't have some of the flexibility that addition and multiplication do. Other phrases that might be C divided by 3. Well, a number divided by 3. Anything else you can think of? Well, like the sum and the difference in the product. For division, we have the quotient of a number and 3. Well, the ones we've done so far here have been just simple, one step, one operation things. Where it gets more confusing is when we have a couple of operations in there. So we might have 4 times a number increased by 9. What is that going to give us? For the number, let's use n. 4 times n plus 9, or 4n plus 9 would be the simplest way to write it. So now I'm going to give you a few to try in your notes. Try those 3 in your notes. I'll give you a couple minutes here. What'd you get for the first one here?
9 plus 4n.
Well, 9 more than means we're adding 9 to something. 4 times the number is 4n. So you have 4n plus 9 or 9 plus 4n. Either one would be fine. How about the next one? The sum means we're going to be doing what type of operation? Adding something. Well, what two things are we adding? 4 times the number, or 4n, and 9. Same as the first two, right? The last one down here, what'd you get?
N plus 9 in parentheses times 4.
Okay, so n plus 9, and yes, we do have it in parentheses times the 4. It could be before or afterwards. Typically, we put it in front of the parentheses. How do we know that that one's different? Well, up here, this first one, it's 4 times a number. So that's why it's 4 times n. Here, it's 4 times the sum, which means we have the result of an addition problem, which means you had to do the addition problem first and then multiply that result times 4. So the parentheses are telling us we have to do the addition part first and then multiply by 4. So as I said, that is one of the more difficult concepts or tasks in math, is to take those phrases and words and put them into an algebraic formula. We saw something like this a little bit in our homework for the order of operations. What does that mean? 8 times 8 times 8. It's called 8 to the third power is how it would be pronounced. And if we would calculate it out as 8 times 8 times 8. Comes up to 512. Well, that one isn't so bad to just put it in your calculator as 8 times 8 times 8. But what if I gave you something like 2 to the 9th? You don't really want to sit there and try to figure out, is that 8 times or 9 times or whatever. On your calculator to do that power, many of you have that caret key like that. Or some of you have a y to the x or an x to the y key. Yours should have a caret key, right?
No, it's not.
Over on the left side, about halfway down, you should have a caret key.
Oh, that one.
Yep. Otherwise, you do have
I'm
it.
looking on the other side.
Yeah, right above it or right below it, you should have an x squared key. For just doing squared, you can use that key. But any other powers, you've got to use the caret key. So to enter that, you would do 2 caret 9 should give you 512. So how many of you have your calculators with you today?
I can't figure it out.
Okay, what model calculator do you
I
have?
have the Texas Instrument 30XIS.
Okay, so on your calculator on the left side, about halfway down,
Oh.
you have that caret key. There you go. You bet. So let's have a little race.
Okay, I got it.
Okay.
It's a little arrow up key. I'm not
Yeah,
technical.
yeah. They call it a caret key, but yeah, it's just a little up arrow. Yeah.
Technology.
I understand completely. So let's have a little race. Let's see if you guys can beat me doing it in my head. 5 to the power of 6. $15,625. How about 4 to the power of 5? Oh yeah, that makes life a lot easier not having to put it in. Like the 2 to the 9th, trying to keep track. Did I punch it 8 times or 9 times or whatever? It's okay. It can be quite a trouble. So that means we can shorten up if we're dealing with variables. If we have x times x times x, we can shorten that up to mean x to the power of 3. Good. If I have something like this, x to the third times x squared, I can actually break that down. X to the third is x times x times x, isn't it? X squared is x times x. Well, if I'm multiplying those all together, x to the fifth. The shortcut, or what's happening there, is I can just take 3 plus 2. It's x to the fifth. So if I wanted to give you something fun, like y to the 12th times y to the 15th, that's going to be y to the 27th. Good. Just 12 plus 15. We don't have to worry about writing it all out and counting them out. So if I want to do operations with these algebraic numbers, we hinted yesterday at 5x plus 11x is going to be, combine the counts, 5 plus 11 is 16. When I add, we keep the same name. When we add or subtract, 1, we combine the counts. 2, we keep the same name. Which implies that they must have the same name. Because you can't keep the same name if you don't start out with the same name. So if I wanted to add 7y plus 12z, what do I get?
19 plus
Perfect. 7y plus 12z, you're exactly correct. They do not have the same name, so we cannot add or subtract them. If I have 5z minus 3z, I'm going to get 2z. Yes. I have the same name, so I can just subtract 5 minus 3. Just like if I had 5 inches and I subtract 3 inches, I'm going to be left with 2 inches. Now here, I look at it, and at first, I see I've got x's and y's. I've got different names. I can't do anything with it. But if I look closer, I realize that there are pieces I can combine. If I had 9 inches and 7 pounds and 4 inches and 3 pounds, I could combine my inches with my other inches and my pounds with my other pounds. Now, there's one big difference here. These are all positive. Here, I've got that minus there. But it doesn't change anything. Remember, we said an operation operates on the number that comes after it. It goes with the number after it. So this addition goes with the 7y. This subtraction goes with the 4x. This addition goes with the 3y. You can actually think of that as a positive 7x. Positive 7y, a negative 4x, and a positive 3y. So I'm going to combine my 9x and minus 4x. So I need to think of that as 9 minus 4 or 9 plus a negative 4. It's the same thing. What do I get? 5x. Because when I add or subtract, I keep the same name. What else can I combine? 7y and 3y make 10y. Now, there's no symbol in between them right now. I have to have a symbol connecting them. Since that is a positive 10y, that's a plus. That is 5x and or plus 10y. I think it was a 5x and a positive 10y. I feel that's easier for you to think of it that way. But the symbol in front of it always goes with the number after it. So since that 10y is positive, this has to be a plus. I don't need the plus up here because it is positive and it's implied. If it were negative, though, I would have to put that negative up there for that number. So here, what can I combine first? 5a and negative 8a makes positive 5, negative 8 is a negative 3a. Good. What else can I combine? Negative 3b and positive 9b. So I've got negative 3, positive 9. And it's a positive, so I'm going to put plus 6b. So we can add or subtract. We can get into more complex algebraic numbers. To do that, I want to look back at our number place values again for just a second. Now that we've talked briefly about powers, exponents, 10 can be thought of as 10 to the power of 1. 100 can be thought of as 10 to the power of 2, makes 100. 1,000 is 10 to the power of 3. 10 to the power of 4 is 10,000. 10 to the power of 5 is 100,000. 10 to the power of 6 is 1,000,000. What do you think is going to go in here? 10 to the power of 0. 10 to the power of 0 equals 1. If you do it on your calculator, it'll tell you 1. The question is why? Remember that power means you're multiplying the number by itself that many times. 10 squared means you have two 10s multiplied together. 10 to the 1 means you have 1 10 multiplied together. There's nothing to multiply it by, right? 10 to the 0 doesn't make sense. How can you take 10 and multiply 0 of them together? Well, you can't. Just like we talked yesterday about multiplying two negatives, the definition breaks down here. So we look at that pattern again. Now, 10 to the power of 3 is 1,000. 10 to the power of 2 is 100. We can see when the base of our exponent is 10, each time we reduce the power by 1, the answer is divided by 10. So let's see if that keeps going. 10 to the 1 is 10. You reduce the power by 1, the number was divided by 10. That works. So now if I reduce the power by 1, 10 to the 0, assuming the pattern continues, what's 10 divided by 10? 1. So 10 to the 0 is 1. In fact, any number to the power of 0 is 1. I could give you 275,000 to the power of 0, it's 1. I've done it to classes. I don't do it in this class because, well, I still have to walk out in the parking lot after class and get in my car. I have done it in classes where I've given problems like what's that have to be? All ones, the power of 0. Yeah, math teachers got to entertain themselves somehow. I say a math teacher implies I'm not a very nice person. But anyway, that's our place values. 10 to the 0 is the 1's place. 10 to the 1 is the 10's place, and so on. When we write a number in that full form or expanded form, one of the ways, instead of writing out 2 hundreds and 3 10s and 8 1s, one of the ways we could have written it is 2 times 10 to the second plus 3 times 10. We sometimes write 10 to the 1 or just 10. Plus 8 times 10 to the 0, or we just write the 8 and leave the 10 to the 0 as implied. That's one way we can write out a number in expanded form, or in that long form. With a whole number written out like that, it looks an awful lot like our algebraic numbers. That is a single number. Now we have fancy names for it. We'd call that a trinomial because it has 3 digits in it, or 3 terms in it. 1, 2, 3. But it is a single number with 3 digits. The place values, instead of being 10 to a certain power, here are x. This is the x to the 0 place value. Well, x to the 0 is just 1, so it's still the 1's place. This is the x to the 1, or just the x place value. This is the x squared place value. Just like here we have 10 to the 0, 10 to the 1, and 10 squared place values. So our algebraic numbers behave exactly like whole numbers, only the place value is a variable rather than a power of 10. So I can take a number like 5x squared plus 7x plus 3. Now those parentheses are not an enclosing symbol here. They are just separating part of the problem, separating that out as that a single number rather than telling us we have to do something there first. But I can add to that 2x squared plus 5x plus 4. And to add those two algebraic numbers, the formal name for them is called a polynomial. To add those two polynomials, I can do it just like I do with whole numbers. Oops. I write out my first number, 5x squared plus 7x plus 3. And then I write the second number underneath it, lining up the place values. The 2x squared goes under the 5x squared. The 5x goes under the 7x. The 4 1s goes under the 3 1s. And now I'm adding. So I've got 3 plus 4 is 7, so that's a positive 7. 7x and 5x is a 12x. Now one of the advantages of algebraic numbers is I don't have to carry. I can have 12x in that place value. I don't need to worry about if it's bigger than 10 I got to carry. Doesn't happen. 5x squared and 2x squared is 7x squared. And that's it. I just added those two algebraic numbers together. One of the difficulties of algebraic numbers that we don't have with whole numbers or integers. In a whole number or integer, either every digit is positive or every digit is negative. For example, negative 293, well, that is a negative 2 hundreds and a negative 9 tens and a negative 3 ones. Every digit is negative. In an algebraic number, each digit can be positive or negative on its own. I can have 3x squared, a negative 9x, and a positive 4 1s. So the middle digit's negative and the other two digits are positive. So that is the second big difference for algebraic numbers. So if I wanted to add that to 5x squared plus 3x minus 11, it's still going to be the same process. 3x squared minus 9x plus 4. 5x squared plus 3x minus 11, and I'm adding down my columns. The difference here is I now have to be careful of my negative. What is 4 plus negative 11? Negative 7. Negative 9x plus 3x? Negative 6x. 3x squared plus 5x squared? 8x squared. So it's no different than adding with whole numbers or integers. If I want to subtract, Same thing. I am just going to line them up like I would any other number. So 8x squared minus 7x plus 9. 3x squared, positive 5x, negative 12. Now I am subtracting down each column. Here's where a lot of students get hung up and struggle. Remember I said yesterday, we're going to go over negatives several times this summer. Well, here we've got 9. This is 9 minus a negative 12. Or that's the same as 9 plus a positive 12. Minus a negative becomes plus the opposite, plus a positive 12. So 9 plus 12 is positive 21. Here I've got negative 7x minus 5x. Negative 7 minus 5 becomes negative 7 plus a negative 5, plus the opposite. So it was minus a positive 5, it becomes plus a negative 5. So negative 7 and negative 5 make negative 12x. And 8x squared minus 3x squared is 5x squared. The process your textbook uses for subtracting, they use a variation of this process here, changing it to plus the opposite. So what they do is they say, well, we're going to take this here and we're going to make it plus, then we're going to change the sign of every digit inside here. So this will become a negative 3, this will become a negative 5, this will become a positive 12. You notice that is what we did. It was 9 and positive 12. It was negative 7 and negative 5. And it was 8 and negative 3. Or 8 minus 3. So it's another way of approaching the same thing. What the textbook does is just a shortcut. Is all it is. Saves a little bit of a few steps. Any questions so far? So when we go to multiply, 9x times 2x gives us 18. Remember, when we multiply or divide, you combine counts. You also combine the names. Which implies we do not need the same name. So here we also combine the names. X times x became x squared. If I had 7x times 4y, even though they are different names, I can still combine them. Combining the count. 7 times 4 is 28. X times y, xy. Because I'm also going to combine the names, I do not have to start with the same name. If I have 9x squared times 5x to the 5th, I'm going to combine the counts. 9 times 5 is 45. Multiplied it. X squared times x to the 5th is x to the 7th. When I multiply variables with exponents, I add the power, add the exponent. Now what if I had 9x squared plus 5x to the 5th? Can I add those? Do they have the same name? Remember, those variables are like place values. 10 squared and 10 to the fifth are different place values, aren't they? This would be 900 and this is 900,000. I technically can add them now that I have them written out like this. But I could not do, 9 10 squareds and 9 10 to the fifths. I couldn't combine them and get like, that should have been a 5 there, shouldn't it? That should have been a 5 here. I couldn't just take the 9 and 5 and get 14 10 to the sevenths or anything like that. That doesn't work because that place value makes them very different in size. So the same here, 9x squareds and 5x to the fifths, even though they're both x, because they have a different power in the exponent, they are different names. So I cannot combine those with addition. Even though I could multiply them, because when I multiply, I combine the names. But here, to keep the same name, which do I keep? The x squared, the x to the fifth? I don't know because they're not the same, so I can't combine them with addition. I can have more than one variable in my multiplication. I could have 8 x to the fifth y squared times 11 x to the third y. I'm going to combine the counts. 8 times 11 is 88. Then I combine each name separately. X to the fifth times x to the third. X to the eighth. 5 plus 3 is 8. Y squared times y. Y to the third. When I have the variable without a power, it's implied to be a power of 1. So it's 2 plus 3. Or 2 plus 1 makes 3. So that's multiplying two one-digit numbers. What if I have more than one digit? Well, if I had something like 24 times 3, right? I would do 24 times 3. This 3 would have to multiply the 4 and then also the 24. And it doesn't matter if I write it as 24 times 3 or 3 times 24. When I go to multiply it out, I'm going to put the number with the most digits on top just to shorten the process. Same thing happens if I have something like 5 times 3x plus 7. I'm going to write that out just like I would with whole numbers. The 3x plus 7 is going to go on top, and then times 5. Just like up here, I did 3 times that last digit. Here I'm going to do 5 times 7, which is 35. It's positive, so I'll put a positive 35. 5 times 3x, 15x. So 5 times 3x plus 7 is 15x plus 35. Now, some of you might be out there thinking, I saw something very different when I took algebra before. Most of you have been taught a process called distributing. Distributing or distribution is just another shortcut for this process. And what distributing is this. You just take the 5 times the 3x is 15x. 5 times the 7 is 35. You get the same result. It's just this way makes more sense to me because it shows the actual process that's going on behind it. Now, with that said, I might do 1 or 2 more examples this long way. Then I'm going to start doing them using distribution in class or just to save time and space as we write. But if you want to keep writing them out long way like this, if that's easier for you, please feel free to just off to the side of your paper, write it out that way and multiply it and fill it back in. So I might have 2x times 3x squared minus 9x plus 13. I do not have to worry about lining up the 2x under the negative 9x because we're multiplying. And when we multiply, we do not need the same name. So 2x times 13 is 26x. 2x times, remember that's a negative 9x. Well, 2 times negative 9 is negative 18. And yes, x times x is x squared. And finally, 2x times 2x squared, 4x to the third. 2 times 2 is 4. X times x squared is x to the third. And that's it. What if I had two-digit numbers? Like 3x plus 7 times 5x minus 2. I can do the same thing. I'm going to multiply them out just like I would whole numbers. I start with the last digit of the bottom number. Negative 2 times 7, negative 14. Move over to the next digit of the top number. Negative 2 times 3x, negative 6x. I put in a 0 or leave a blank down here, and I move over to the 5x. 5x times 7, 35x. It's positive, so I put a plus 35x. 5x times 3x, 15x squared, yes. 5 times 3 is 15. X times x makes x squared. So now negative 14 and 0 is a negative 14. Negative 6x and positive 35 is a positive 29x. And 15x squared. Many of you were taught a drastic shortcut for these types of problems when you were younger. Something called FOIL. FOIL is just a little mnemonic device that takes you through steps that do this. F stands for first. You multiply the first two digits in the numbers. 3x times 5x is 15x squared. O stands for outside. Multiply the outside digits. 3x and a negative 2. 3x times negative 2 is negative 6x. I stands for inside. You multiply the inside digits. 7 times 5x is a positive 35x. And L stands for last. The last digits. So 7 and negative 2 multiply make negative 14. Then, of course, you still have to combine like terms, things with the same name. Negative 6 and 35 still make a positive 29. So you get the same result. Now this way is much, much shorter. This way makes way more sense to me. But again, we'll do it this way a few times in class, and then we'll come back to just using the FOIL method shortcut just to save time. If this way makes more sense to you, feel free to go and use it that way. Okay, it is time for a break, so let's go ahead and take 10 minutes here. And let's come back about 10:31 and we'll start again.